everyone. My name is Sadia Afroz. I'm a researcher at the International Computer Science Institute in Berkeley. In the last couple of months, I have been collaborating with Avast for doing adversarial machine learning attack on Malware Detector. And I liked working with them so much that I'm joining them to spend more time there. So this talk is about what we have learned so far while trying to attack malware detectors. Nicola gave a great talk about how adversarial attacks work. Just to recap, typical adversarial attacks work like this. You take a machine learning model that has a very high accuracy to do some task. For example, here, a bird classifier that can take a bird picture and tell you that this is a bird. But then, if you modify the picture very slightly by adding some special noise to it, the bird picture still looks like bird to us, but the classifier will make a very high confidence mistake and think that this is a horse. This is a very surprising attack, because without the modification, the classifier works very well, right? And it could be a devastating attack that can affect all of our lives. Let's suppose you're in your self-driving car, and the stop sign classifier in your car considers it as a speed limit sign. And this is not a far-fetched attack, by the way. My colleagues from UC Berkeley already showed that you can modify a stop sign by adding black and white stickers to it, and a classifier will think that this is a speed limit sign. Researchers have shown this attack in many other domains. For example, in the audio domain, you can add a little bit of noise to open the door, how are you, and it will become open the door. There's also attacks that showed you can wear a special pair of sunglasses with special patterns in them, and the classifier will think that this is Mila Jovovich. Now, when we hear about these attacks, they seem very futuristic and theoretical. Academics toying with their machine learning models, tweaking different pictures. But actually, these attacks are already happening in the real world. For example, you probably have noticed that spammers tweak their spam messages a little bit to evade spam filters. That's a real-world adversarial attacks. There are YouTube videos that add special patterns to them to evade YouTube's automated content filtering. In the malware domain, we have very dedicated adversaries who are always trying to change their malware to evade malware detectors. There are ransomwares that put on some benign characteristics, for example, getting signed by trusted authorities to bypass malware detectors. So how do adversarial attacks work in the malware domain? The attacks are very similar in concepts to the image domain. Here, we have to change some code by adding some other stuff to it. But even though these attacks are very similar in concepts, there are some fundamental differences between these two domains. First of all, adding and deleting some pixels to an image does not change that image so that it's beyond recognition. But adding and deleting a little bit of code from a malware might make it not a malware anymore. Most importantly, though, evaluating an adversarial example for images is very intuitive for us. For example, if a classifier cannot find a duck in the picture on the right side, none of us would be surprised because we cannot see a duck there. But if I tell you that the left side, this is an original malware code, can you tell me if the right side is a malware code or not? No, because evaluating malware takes a lot of time and effort. And in some cases, it could be impossible because we need to recreate an environment where the malware can work. Maybe these are some of the reasons why we don't see that much research work on adversarial attacks on malware detectors. Adversarial machine learning is a very rapidly growing field. And since 2014, there's been more than 1,200 papers on adversarial machine learning. But only 36 papers focus on malware. Even though we know that in the real world, real adversaries are trying to evade these malware detectors. So let's see more details about how adversarial attacks work. If you have an unlimited access to a malware detector, you can modify your malware and query the detector and continue the loop as long as the classifier thinks it's benign. If you don't have access to a malware detector, as Nicholas shows that transferability works for machine learning models, you can tweak your malware to a substitute classifier or an ensemble of classifier and use the example that evaded all of those classifiers to query the real malware detector you want to evade. So how can we modify a malware? You can modify a malware in any ways that does not change the functionality of the malware, right? So you can add random padding to it. You can add benign files to it. One popular benign file to add to a malware is the Microsoft software license terms, because many of the benign files already have that file. You can also add malicious functionalities to a benign file. There's research showing that this attack is more useful than the other way around. You can also encrypt and compress a file multiple times using a packer to evade signature-based classifications. So now, after we made these changes, how would we know if this is a valid adversarial attack? The current way to figure this out is this. You ask a malware detector before modification, is this a malware? And then you apply your modification and ask it the same question, is this a malware? And if the malware detector thinks it's a malware before the modification, but does not think it's a malware after the modification, then we consider that the attack is successful. This is a great way to evaluate your adversarial examples if this is an image, because for images, we can verify valid adversarial attacks just by looking at them. But it's not enough for malware, because for an adversarial malware, the main question we want to ask is that, is this modified malware still malicious? And unfortunately, just the answer of the malware detector does not help us answer this question. So let's see two examples in cases where the modified malware is not malicious anymore, but it evades classification. Let's consider this malware. It connects to a command and control server and does something malicious after it receives the command. If you ask a malware detector if this is a malware, it has never seen this file before, so it's going to do static and dynamic analysis to the file, create a signature, and consider that this is a malware. Now, after it has seen this file, since there's already a signature for this file, it will try to match the signatures of the file and consider that this is a malware. After creating this signature, the malware detector will always match the signature instead of doing any kind of complicated analysis. Now, let's consider 5 years have passed, and the CNC server is dead now. Is this still a malware? Depends on who you ask. If we ask the same malware detector if this is a malware, notice that the signature of the file hasn't changed. So it's going to consider it as a malware, even though it's not doing anything malicious now. Now, let's do our adversarial attack on this piece of malware. Now, the signature has changed, so the malware detector does not have any signature to match. So it's going to do the analysis of this file and consider it as benign. And it will be correct, because this file is not malware anymore. This is a very likely thing to happen, by the way, because most malware research use 5 to 10-year-old malware sample, and many of them might be inactive by the time when we are trying to do adversarial attacks on them. And that's understandable. If you're an academic, having a very active malware samples all labeled are very hard to come by. But using old malware that might be inactive has its own consequences. The second reason why a modified malware might evade detection without being malicious is corrupted malware. There are some malware that are packed in a way that if you just change one bit in them, it's just going to destroy the entire file. So if you ask a malware detector if this corrupted file is a malware, it's going to do analysis and does not find anything in it because the file doesn't open to do anything malicious and consider it as a benign. So now the question is, what kind of attacks should we focus on while we are doing this adversarial attacks on malware detector? Adversarial attacks are a great way to debug machine learning-based malware detectors, but we need to focus on the attacks that are real adversarial attacks and that can help us understand shortcomings of our malware detectors. So one way to to find valid adversarial examples, it starts with an active malware that evades detection. And how would we find these active malwares that evade detection? We need to perform our attack on the files and analyze them. However, current research in machine learning, adversarial attacks on malware detector does not help us answer this question. Remember, in the beginning of my talk, I told you about these 36 papers that perform attacks on malware detector. About 25% of them did their attack on malware files. The rest of them did the attack on the feature vector. About 5% of them tried to execute the file by clicking on the file. But 0% of the paper checked whether this malware was actually harmful or not. In some cases, just clicking on the file and watching that the file works is not enough to figuring out whether this is still malicious or not. So how can we do better? First of all, for adversarial attacks on malware detectors, we need to start with active malware. Now, finding active malware is very hard, but we can start with malware that are recent instead of very old. And we need to perform, we need to analyze them on a virtual machine and open source dynamic analysis to figure out that they are still active. These things are much more time consuming, but they can be automated. And at least this way we'll make sure that the adversarial attacks we are doing are valid adversarial attacks. The second thing we need to do is we need to execute our attack. And again, analyze them on a virtual machine and with with open source dynamic analysis. Depending on the goal of your research, checking against a real-world AV might be a useful thing to do. Sometimes the goal of adversarial attack on malware on machine learning is just to find specific problems with a specific machine learning algorithm. In that case, checking against real-world AVs is probably not the best thing to do. But in other cases, if you want to know what kind of attacks we want our users to protect against, real-world AVs can help you answer this question. This way, we'll make sure that we are not doing research that these commercial systems have already solved. Now, if we want to analyze all of our adversarial examples using real-world AVs, we have to send all of our adversarial examples to these AVs, and that might pollute their training data and make them worse to defend against real attacks. So doing this safely is still a challenging problem. Now that I told you that current attacks does not help us answer the question that what kind of attacks are useful, there are already adversarial attacks happening in the real world. And are we prepared for these attacks? There are a lot of defenses proposed to defend against adversarial attacks. I will talk about two of these defenses. The first defense is adversarial retraining. Recall how adversarial attacks works. You have to take malware and modify the malware so that enough times so that it evades malware detector, and the malware detector considers this as benign. Adversarial retraining tells you that after you have this benign sample, you retrain your classifier with that sample. Adversarial retraining can help us identify examples that are easily evadable adversarial examples. But the problem is that it can also decrease your accuracy. So here in the graph, we show how adversarial examples can increase the robustness of the classifier, but decrease the accuracy of the classifier. This experiment was done on a digit recognition dataset. Here, the x-axis shows the number of adversarial examples we added. The blue curve shows the accuracy of the classifier, and the green curve shows the robustness of the classifier. By robustness, I mean how many features you need to change to evade the detection. Without any adversarial example, the classifier is very accurate, 97% accurate, but it's also very brittle. You need to change only 10%, only 10 pixels to change the classifier's decision. After you add about 0.1% adversarial examples, the classifier's robustness increases, but it also decreases the accuracy of the classifier. This happens because as we are adding more and more adversarial examples, the classifier gets tuned to classify only those adversarial examples, and it diverges from the naturally occurring examples. To defend against this, we need to make sure that adversarial retraining does not diverge too much from the original examples. The second defense I'll talk about is building classifiers that are robust by design. Let's consider this malware detector is a logistic regression-based malware detector. It has some features from benign files and some features from malicious files. Whenever it gets a malware file, it analyzes this file and gives it a score based on the number of malicious feature this file has and number of benign feature this file has. Let's suppose in this particular case, this file gets a score of 3.2. It will be considered as a malware because the score is positive. Now, let's think for a second. If you were an adversary, how would you evade this classifier? The easiest way to evade this classifier is to add a lot of benign files to it. In that case, since the classifier is always weighing number of benign features to number of malicious features, and now we have increased the number of benign features a lot, it's going to consider that this is a benign file. So how would we defend against this kind of attacks? One way to defend against this kind of attack is using monotonic classifiers. Monotonic classifiers ensures that attacker cannot change the classification score by adding a lot of benign features to it. This graph here shows a typical classification score of a classifier. Here, the x-axis shows the feature values, and the y-axis shows the classifier score. And you can see that as we are adding more features, the score of the classifier can increase, but can also decrease. Monotonic classifier ensures that the score of the classifier can never decrease as you're adding more features. Here, the red curve shows the monotonic classifiers. And as you can see here, even if we add more features to it, the score of the classifier is never going to decrease. We proposed this classifier in 2017. Now, this seems like a very simple defense, but actually, adding features to evade real-world malware detectors is an attack that our real-world adversaries are already doing. Many of you might remember that researchers showed this attack against an AI-based malware detector, Cylance, and their attack was also very similar. They added a lot of benign features to their malware. So how can we make this classifier, the logistic regression-based classifier I showed, as a monotonic classifier? We can turn this classifier into a monotonic classifier by just considering the malicious features. So in this case, even if you add a lot of benign features to it, the classifier will not consider it as benign because we are not considering any of the benign features at all. This is not a theoretical defense. After we published this paper in 2017, Microsoft Defender ATP has adopted this monotonic classifier, and they're using it to defend against real-world ransomwares. This is, by the way, just only one way to implement monotonicity. There are many other ways to implement monotonicity. In the paper, we talk about using only monotonic features. For example, features that can be only added but can never be deleted. For example, writing files. If a malware has to create a certain amount of file and write in a registry keys, it cannot remove those functionalities without removing the maliciousness of the file. So monotonic classifiers by themselves have lower accuracies than regular classifiers. And that's understandable because to ensuring monotonicity, we are constraining the classifier. We're making sure that it has certain properties. Here, you can see that the monotonic classifier has lower accuracy, which is shown in the blue curve, than regular classifier, shown in the red curve. So one way to solve the problem of having lower accuracy is using an ensemble of classifier, so that in that case, if any of the classifiers consider a malware as a malware, we'll declare that this is a malware. So to conclude, adversarial attacks is a great way to debug machine learning models, which might seem like an opaque black box when we're using it. But while we are doing adversarial attacks in the real-world malware detectors, we need to make sure that the attacks are valid adversarial attacks. For malware detection, we need to ask, while we're validating our attack, we need to ask what kind of attacks are really harmful to the users. Fortunately or unfortunately, in the malware domain, we have real adversaries that are doing adversarial attacks. So studying real-world adversaries can help us identify what kind of attacks are useful. So that was my talk. Thank you.
Sadia, thank you. And I have questions for you. Do you have a rough estimate of the percentage of malware in the wild that uses adversarial evasion?
No, I don't. But I'm sure a lot of them are doing it. And that's one of the questions we are trying to figure out.
There is also one comment from Professor Cavallaro, his super biased opinion, that there is a poster upstairs touching the topic of adversarial ML in the problem space. But let's go to the next question. Does the research in the area check if the evasion attacks work against pattern matching detectors, non-ML?
Research in the area check if evasion attacks pattern matching detectors. Yeah, I think so. It will, because you just need to figure out what pattern you're matching and then make sure you are using different patterns.
And could you use old labeled malware and simulate their CNC servers?
It's probably possible to use old malware, but you need to know what the CNC server was doing to trigger the malicious activities in the old malware. And in some cases, it could be difficult if we don't know what was the activity it was supposed to do.
So thank you. I think we have answered everything.
Okay.
Thank you very much, Sadia.
Thank you.